Welcome to the Clear to Send podcast, a podcast about wireless engineering, where we educate you on Wi-Fi technology, talk about design tips, troubleshooting, interviews, and the tools. Here are your hosts, Roel and Francois.
Today's show is brought to you by Audible. Audible is offering our listeners a free audiobook with a 30-day trial membership. Just go to audibletrial.com/clear2send and browse the fantastic selection of audio programs. Download a title free and start listening. It's that easy. Again, go to audibletrial.com/clear2send. Hey everybody, welcome to a brand new episode of the Clear to Send podcast. I am Roel Dionisio, and we have here our co-host, Francois. How are you, Francois?
I'm very good. Hi, Roel. How are you?
I'm doing good. It's actually warm today, early in the morning, and this summer, but it's not as hot as the rest of the country. How's the weather on your side?
Right, it's raining today here in Canada, but it's not cold. It's warm too, so it's nice.
Okay, it's not quite how I feel here with the weather. I feel like it's raining on my end only because I have this pretty bad cough, so I'll try not to cough during the recording. And that's why my voice sounds a little bit different, because I'm losing it just a little bit.
Sick in the summer, huh?
Yeah, it's not the best thing.
It happens, okay.
Well, we have a pretty good episode today, I think. And one of the first things I wanted to bring up is this new AP that Ruckus Networks came out. It's the R730. What do you think about it?
Well, it's nice. It's the first AX AP from Ruckus. And they're advertising 8 streams on the 5 gig band. So we're starting to see some AX specs, OFDMA, multi-user MIMO. So it looks good on paper.
It does, yeah. And most importantly, it's going to support WPA3 and Wi-Fi Enhanced Open, both from the Wi-Fi Alliance.
Yeah, which is nice. That's nice that they, advertise that in the data sheet.
Yeah, it's like right up front on the first paragraph of their announcement. And I was really interested to hear that they're going to support Wi-Fi Enhanced Open, because, as we know, it wasn't part of the WPA3 certification. And so I think for them to add this into their AP, it shows that even though it's an optional thing, I felt that Wi-Fi Enhanced Open, for those of you that don't know, it's the OWE, and that helps protect open Wi-Fi networks. And I think this is a great addition to securing Wi-Fi even further.
Yes, it's nice to see manufacturers taking it in seriously and putting that feature into their APs.
So we'll see once this comes out how much of these certifications it actually supports, because this is what I'm most interested in. It's nice to see that it supports a lot of spatial streams. I think in this announcement it says 12 spatial streams. I don't know where.
Because they're adding 5 gig and 2.4.
Oh, okay, I got you.
Yeah, they have 8 and 5, and then 4 and 2.4. Oh.
All right, so we'll link out to the announcement and the data sheet just so you guys can take a look at this, because it is 802.11ax, like we said. It's going to support WPA3. We don't know which parts of WPA3, and also Wi-Fi Enhanced Open. And so I'd like to play around with Wi-Fi Enhanced Open just to see how it works with clients that are out there. What does that frame exchange look like? I mean, it's all in the standards there, and not the standards, but the IETF. If you look that up. So we'll also link out to WPA3 and Wi-Fi Enhanced Open, just so you guys want to take a read of how this all plays out.
Also, I'm interested with all those AX APs. I'm interested to see how they will play in a high-density environment, because here it says that it will manage more than 1,000 client connections. That's crazy. If, in our regular environments, APs don't support that many clients.
Right, and just pure physics of things, right? Your airtime. Yeah. How's that going to affect airtime?
Yeah. I don't know. And you also have, active clients versus just associated clients. So I'm not, they're probably talking about associated client. But still, like 1,000 it's a crazy number.
It is.
So I don't know if it's just marketing or if it's something we'll be able to see in the future.
Yeah, is this just more marketing, or how are they doing this? Because they do say airtime decongestion, and so it's saying it increases average client throughput in heavily congested environments by using patent-pending techniques to reduce unnecessary management traffic. So what does that mean?
That's
Maybe
a good
somebody
question.
knows. I don't know. I don't know yet. I haven't looked that into it, but it sounds very proprietary since it's patent pending. But maybe it works. I don't know. I mean, Cisco has a lot of proprietary stuff in their technology as well.
Yeah.
All right.
Right. It looks on paper. It looks like a very good access point. The design looks very old, though.
Yeah. They stuck with the very old design that they've been using. Everyone else is moving to these fancy looking APs, but they stuck to this. Looks like a wall sconce or something. All right, so why don't we move into this new segment we're going to do for the next couple of weeks, Francois?
Yeah, so we've been doing some recordings, presentation recordings of some Wi-Fi engineers out there. We started at Cisco Live. We interviewed a few people. The goal was to present Wi-Fi engineers to the community in a different way. It's more on the personal side of things. So we asked 10 quick questions, and then they didn't know the questions before we asked them, obviously, and then they answered them. Just quick question, quick answer type of interview, and then you took a picture of them so we could create a profile and then share it with the listeners and the community. So today we're going to listen to our first interview. This one was interview of Jason Bashara, and you can listen to it right now. What's your name?
My name is Jason Bashara.
Where do you currently live?
I currently live in Atlanta, Georgia.
Where were you born?
Youngstown, Ohio.
What is special about that place?
There are many special things about Youngstown, Ohio, two of which that stand out are the food and the mafia.
Okay. What is your job, and why do you do the work you do?
My job is a post-sales engineer for VAR here, and I do Wi-Fi because I love it and I'm passionate about it.
What would you do if you were not doing wireless?
Hopefully I would be off on a fishing charter somewhere being a captain.
Okay. What could you give a 40 minutes presentation on without absolutely no preparation?
Industrial Wi-Fi.
What is something you think everyone should do at least once in their lives?
Jump out of a perfectly good airplane.
What do you think your job will look like in 10 years?
Hopefully retirement.
Thank you, Jason. All right, so that was the first one. For Jason, actually, he knew the questions because we had to do it twice. That was the first time around. But all the other ones, they didn't know the questions.
I don't know, Francois. Would you jump out of an airplane?
With a parachute, maybe, yeah.
Yeah, I think I would do it too. It's pretty scary, but I did like that response. And what we'll do in the show notes is I'll add his profile picture. I was the one that took the profile shots of everyone during Cisco Live when we interviewed them. I brought my camera along with me, and then we'll also add a link to where you could follow them on social media. And I thought this was a cool thing to do with people in the community to figure out or know how people are besides the tech side, right? Besides knowing that they do Wi-Fi.
Yeah, and I think we have about 20 of them. And we might do another series, at a future conference or something. We just have to update the questions. It's better if the interview doesn't know the interviewee doesn't know the questions.
Yeah, so the responses will get better as we go on in the next couple of weeks.
We'll see. The captain was a pretty good answer.
It was.
We get pretty funny answers, so you guys will see. Stay tuned.
Yep, stay tuned for the next ones. All right, so let's go into our main segment here. We're going to step back and go into the fundamentals, the basics of wireless. And the best place to start is to talk about RF characteristics. And this is where I think a lot of people should start when it comes to Wi-Fi, or just to know about Wi-Fi and how it works, because a lot of this can help you in troubleshooting, actually, because a lot of this applies very much into the real world, even if you just knew some of the basics. Would you agree, Francois?
Yeah, most people working in wireless, they come from the networking side, so they're very strong in, layer 3 and above, I would say. Even layer 2 and above, VLANs, IP addresses, subnetting, routing, and you name it. So most of the work you need to do if you're getting into wireless is to get stronger and learn your basics, your RF basics, the layer 1. Some people they're coming from the RF sides, and then they're coming from the RF sides, and then they're doing Wi-Fi. So that's the other way around. They have to spend more time studying networking and IP and all of that, right?
Right.
But most people, they come from the networking side, and then they get involved on Wi-Fi projects. So it's a really good a really good place to start. Get your RF fundamentals solid. And that's pretty much what we're going to go through today, the different RF characteristics, frequencies, and wavelength. We're going to go through those characteristics and explain how we use them in Wi-Fi, how they're used in Wi-Fi to pretty much transfer data. And we'll also go through some RF behaviors that those RF or those frequency waves are going through when they're going from one transceiver to a receiver.
Yeah, and that portion will help you in also placing your access points. So why don't we get into this? It's going to be a summary or overview of this. We're not going to go into that much in depth in such a basic discussion of this, but RF being the first one, if you don't know, RF stands for radio frequency. And specifically, we're talking about where Wi-Fi operates. So currently, Wi-Fi operates in an unlicensed radio frequency. That means anyone who builds equipment with that's Wi-Fi capable can operate in that license or in that frequency. Whereas there's different frequencies that are licensed. You have to have a license to use those through the FCC, as an example. And a lot of those could be things like point-to-point connections, radio connections.
The most common example would be cellular networks. Like a cellular company, they have to purchase a license in order to be able to use certain frequencies. But once you have purchased a license, you are the only one authorized to use the frequency, so you don't have to deal with interference and with interferencing with other system or other technologies. Whereas Wi-Fi is used is using unlicensed frequencies, which means that other wireless technologies are also using those frequencies, and you might have interference.
Exactly. So that's why we have cameras that work over Wi-Fi. We have door locks. Microwaves operate on this unlicensed frequency. Another example of licensed frequency, it could be AM FM radio. We use that every day, right, in your car. That's a frequency as well that travels.
Yep.
AM travels very far because it's got a much shorter, I guess we'll go into this now, much shorter wavelength compared to Wi-Fi frequency that it operates in. And Wi-Fi operates in 2.4 and 5 gigahertz for now.
It has a lower frequency, so a longer wavelength.
Where Wi-Fi has 2.4 gigahertz and 5 gigahertz, it's a much shorter wavelength, so that's why you don't see it penetrating through trees, for example. It doesn't do that very well compared to AM radio, and that has a much shorter wavelength. I don't even know what the exact wavelength is, but I know it's in the
I think it's in meters.
Sub-100,
yeah.
And then what you have is a carrier signal that takes this AC signal and turns it into a waveform, which is an electromagnetic waveform that travels through the air, and that's our Wi-Fi signal. And there's a modulation that changes that signal to create that carrier signal, so that way these Wi-Fi devices can understand what this frequency is. And that's why our laptops or mobile phones, they don't demodulate the AM signal or FM signal or even microwave signal. Microwave doesn't have a modulation that our laptops and devices would be understand, right? They don't really see it at contribute to, say, the SNR, because it's not a signal that our Wi-Fi devices understand what it is.
Yeah, how I usually explain it is, RF will have different, like a radio frequency signal will have different characteristics. I always name for them a frequency, wavelength, amplitude, and phase, right? So that's 4 different RF characteristics. And in order to send bits, so zeros and ones over this RF wave, we're going to modify some of these characteristics in order to represent zeros and one, right? Depending on the wireless technology you're using, you're going to choose to change the frequency or change the amplitude or change the phase and so on. In Wi-Fi, we change the phase, or we change the phase and the amplitude, so that the type of modulation is used in Wi-Fi.
Yeah, and so you mentioned wavelength, and I think that's always the first component of RF that people should know, because if you think about like waves crashing onto the beach, like that comes in at an interval, right? You always see these waves, they peak at the top. You can and when you see those waves, depending on how large they are, that's what I would consider like the amplitude, the strength of that wave. And so Wi-Fi waves are very similar, where you have these what you call like a crest or a peak, where it reaches the top, and then you have these troughs where if you have a line, like a horizon line, they go under that line, and you'll have the distance between 2 identical points in that wave, and that is your wavelength.
Yeah, distance is a key word for me in wavelength. It's actually something you can measure, right? Wavelength is the distance between 2 cycles, right, or peaks or waves. And it's actually something you can measure in depending on the frequency. It would be in centimeters, in inches, for the guys in the US and Canada, in meters, in miles, in yards, or whatever. But it's actually something you can measure. Just to give a reference example, in Wi-Fi, if you're using 2.4. The wavelength would be 4.92 inches, and if you're using 5 gig, the wavelength would be 2.36 inches.
Yeah. So then if we talk about amplitude again, to go into a little bit more detail, amplitude is the strength of the wave that's being transmitted by that Wi-Fi device. And as that signal leaves the transmitter, that's at its peak, its highest amplitude. And as it travels through the air, it starts to attenuate, which we'll talk about, and it'll start to lose some of that amplitude as it goes through the air and being received by the receiver. So the higher the amplitude, the better the chance the receiver has at demodulating that signal.
Yeah, amplitude is the power. How much power how much energy you carrying through this RF wave. So amplitude is ready to power. When we talk about power in Wi-Fi, we always talk about the transmit power and the receive power, right? So the transmit power is usually what we set, a configuration we set on the AP side, and it has a specific value. We usually express this transmit power in dBm or in milliwatts, right? Sometimes in watts. And then we have the receiving power, which is pretty much the signal strength of the signal we're receiving. We usually call it the RSSI, right? And that's we usually express this value in dBm.
Yep. And when you talk about this amplitude from the AP side, your transmit power, you always got to remember, what is my regulation in my country as far as how high can I transmit that signal, and hopefully your wireless system actually will not let you transmit beyond beyond your regulation. But
well, if you set the right country code, yeah, and if they're programmed properly.
But that's the best way to think about amplitude in a Wi-Fi sense. If you're dealing with the Wi-Fi equipment, is that transmit power, and then the receive power, like Francois said, is basically what we think of as RSSI, which there is no standard as to how you determine RSSI. Most of these vendors determine RSSI, the value itself, based on their own proprietary math calculations. But generally, that's what your received signal is RSSI.
Also, we're talking about amplitude. Maybe we can compare, Wi-Fi power versus other wireless technologies.
Because Wi-Fi power is not very strong.
Yeah, so usually as a transmit power, we're going to use 50 milliwatts, sometimes 25 milliwatts, sometimes 100 milliwatts. Depending on your regulation, the maximum would be 200 milliwatts or 1 watt, depending on the frequency band and where you live in the world. So we're talking sub 1 watt type of power. If we take the cellular networks, for instance, the base stations, they can be configured between 10 watts and 500 watts for the transmit power, which is, much more powerful already. And then if we talk about microwaves, how sometimes you can change the power on the microwave.
Yeah.
And it's like between 700 watts and 1,000 watts.
Even 1,000, yeah. And I like to use that comparison because people use microwaves all the time. So, like if you think about microwave, we're not talking milliwatts, we're talking watts. And so microwaves can cook food at 1,000 watts. So that means if your face is standing right in front of that window, that's not a good thing to do, especially if that microwave's shielding. So microwaves have shielding around it to control where that power, that amplitude is going. And so it's not supposed to leak out of that microwave often. And you could see this with a spectrum analyzer, right? So if someone starts microwaving food, you could see that amplitude peak in the 2.4 gigahertz spectrum. And that's at thousands of watts. Wi-Fi operates in just milliwatts, which is 1/1000th of a watt. So much, much less amplitude coming out of Wi-Fi transmitters. And devices devices aren't as powerful when it comes to the amplitude out of, say, a laptop or a phone. The power transmitting out of those devices is not as strong as, say, a transmitter on an AP.
Yeah.
So the next one is frequency, which typically we all understand because we operate Wi-Fi in 2.4 and 5 gigahertz frequency. It's a much higher frequency within the radio frequency spectrum. And this is just a number or an interval which a wave actually repeats or oscillates is the right term to use. And that's just the number of wave cycles being repeated. And usually what that also means is the higher the frequency, the wavelength is shorter, which we discussed under wavelength, which is why 5 gigahertz just doesn't 5 gigahertz will attenuate much more easily through, say, drywall than 2.4 gigahertz.
Our show is brought to you by Audible. Did you know you can ask Alexa to read a book to you? I have an Alexa Dot in my house, and I had my favorite book being read to me, Ready Player One. It was really awesome because audio makes great audiobooks, whether you like to listen to books to get your mind somewhere else or whether you like to learn. Sometimes I like to read biographies. I've been an Audible listener for over a year, and I absolutely love it for my commute. You will too, because the selection on Audible is phenomenal. It seems like every book that comes out in print is also in Audible. So for you guys, you can go to audibletrial.com/clear-to-send, and you can get a book for free right now. Download it and start listening within a few seconds. So again, that's a free book for you guys. Download it at audibletrial.com/clear-to-send.
So the frequency is expressed in hertz, and 1 hertz is 1 cycle per second, right? Here in Wi-Fi, we're talking about 2.4 gigahertz or 5 gigahertz. So it's 2.4 billion cycles per second, so 5 billion cycles per second. So you can try to imagine the speed, the frequency of the wave. Like you mentioned, Roel, wavelength is even inversely proportional to frequency. So the higher the frequency, the shorter the wavelength will be, and then the lower the frequency, the longer the wavelength will be.
Yeah. Yeah, and we're talking gigahertz. So if you compare this to FM radio is between, say, 88 and 108 megahertz. And so that wavelength is much longer than Wi-Fi frequency.
Yeah, and then wavelength, we didn't talk about that, but it will also impact the size of the antenna. I believe your antenna has to be a minimum a quarter of the wavelength of the signal you're trying to listen to, right? So if you have a lower frequency, the wavelength will be bigger, so the antenna will be bigger. So typically 2.4 antennas are bigger than 5 gigahertz antenna.
So that's kind of the gist of frequency, and there's honestly a lot of different frequencies in this space, and Wi-Fi has a small sliver of these frequencies that are being used, which depending on where you are in your country, for example, the U.S. has FCC that controls what operates on what frequency.
Yeah, and but all these concepts can be applied to other frequencies as well.
And then we have phase, which is it's not really a characteristic per se of Wi-Fi. It's really comparing two RF waves, because you could have waves that are in phase or out of phase. And what that means is in Wi-Fi environments, like in an office space, for example, with APs nowadays, you have multiple antennas, you have multiple radio chains on your devices. And as these waves get propagated, they can bounce around, right? So we'll talk about some of these different behaviors that could happen. But your device can receive that same signal multiple times based on how that signal was propagated through the air. And as your device is listening for these waves, it can receive, let's say, 2 of the same wave, but maybe not at the same time. And so in phase means that those 2 waves, what's the best way to say this, like Francois, that they're aligned, and that would be in phase, and that would mean like the signal is stronger, versus out of phase where it could cancel out each other.
Yeah, so that's if you're using multiple signals. If we focus on just one signal, right? The phase corresponds to how far the signal is offset from a reference point. So let's say you have your carrier wave that has a reference point. A phase is expressed in degrees. So one cycle would be expressed in 360 degrees. You can see it as like a circle, right? And then you start again. So 0 to 360 degrees. If you offset this wave from like 90 degrees, it means you're moving pretty much the wave 90, so a quarter of the cycle, right? 90 degrees would be a quarter of 360, so you're moving the wave a quarter of the cycle, and usually we change the phase of a wave to represent information, right? To encode zeros and ones to modulate. So
this part's hard to visualize with any tools that we have, unless you've got really expensive equipment that can do this.
Yeah, I think you can do it with very expensive equipment. Well, I mean, it's not too hard to draw it on a whiteboard. You can explain how to represent zeros, ones, changing the phase.
Because this goes with the modulation that's being used by your APs and devices.
Yeah, that's usually how you use the phase. It's to modulate signal to represent data. One way to see it is if you shift your phase 180 degrees, that's pretty much half of your cycle. You pretty much reverse the wave, right? So that's one way of saying it.
Yeah, we'll have to include some photos because it's very hard to describe over audio.
Yeah, over audio, it's a challenge. But it's a very important concept.
Yeah, because it does affect the way you receive the signal from a transmitter, but we can add some resources in there to help describe better how phase actually affects RF and what it does with modulation and what happens when a device receives it, for example. So we'll add some resources onto the show notes there. So the last part, which we'll kind of go over fairly quickly because I think we can easily describe these are what happens when signal is transmitted through the air and how does it change if it does change depending on the environment. And so there's a number of different behaviors that could happen. The first one that's common in maybe like warehouses, for example, is reflection. I mean, it can happen in any environment, but reflection is when signal bounces off another object. Like, for example, if you point a flashlight at a mirror, that light will bounce off the mirror and then into a different direction. So that's an example of reflection.
Yeah. What's hard for us as human being for all these RF behaviors we'll be talking about? It's almost impossible for us to how can I say that to assess them, or we cannot see them, we cannot feel them, we cannot even if we can calculate them. Mm-hmm. Right? So it's very hard for us to understand.
Yeah,
well, I mean, we can understand them, but it's hard for us to
model it. Like you can't.
Yeah.
It's hard to put this into a design and do a predictive design and say this is how much reflection is going to happen in this environment.
Yeah, exactly. You kind of have to go as you feel. But yeah, I mean, the physics is pretty straightforward. But in the real life, if you enter in an environment, in an office, in a stadium, in a warehouse, you never know how all of this will impact. Mm-hmm. Exactly how it will exactly impact your the signal coming out of your AP.
Yeah, and I think some of these we can measure. For example, I'll skip down. If we talk about absorption, right? This is how RF goes through varying materials, and this is when the signal loses its strength, its amplitude, or it attenuates going through something like drywall or concrete. And I think a lot of people forget to accommodate absorption because they'll put the access point next to something that basically absorbs the whole signal, right?
Yeah.
Or they'll put it in, say, like a full metal enclosure where it's actually just reflecting the signal inside the enclosure and it's not going through.
And when we talk about absorption, there is the interesting physical fact here is so the energy will come towards this surface, right? And then the surface will absorb some of the energy, and so you're gonna have you're still gonna have energy going through the other side, but it's just gonna have a lower amplitude. And then the energy that's absorbed by the object or whatever you have will be transformed into heat, right? So the example I often give is, let's say you have sun going through a window. You're gonna have a heat coming from the sun, and then the window is gonna absorb some of that, and then the window is gonna become warm a little bit depending on the temperature. But sometimes you can feel it.
Yeah, and if you look at microwaves because they're blasting RF at 1,000 watts, that's how your food gets heated.
Yeah, exactly. Yeah, the water absorbs the wave and transforms it into heat.
Yeah. That's why we have regulations around how strong of a power APs can transmit at. We don't want them transmitting at 1,000 watts.
I don't know what will happen.
We'd cook. So then next we have refraction, which for me is hard to get someone to understand, especially in an office environment, because this is just when signal bends when it goes through a different medium. So the biggest example is if you're looking at a glass of water and light is going through the glass of water, you'll notice that it actually changes the direction once it leaves the glass. It changes the direction of the light, and it's bending that light in a different direction. And I think most of this actually happens in outdoor wireless. Say you have a lot of fog, or even the oxygen can affect the signal, especially in the much higher frequencies. But refraction for like office environments, I don't know if that happens very much.
I don't think so. But with IoT and stuff, you might have now in
like like in a water
They
tank
might
or something.
They might put sensors in aquarium or something. I don't know.
Yeah. So this one's hard for me to describe to people unless they're. I always think about. Actually, it could happen in glass, right? Depending on the type of glass that you have in your environment, it could bend the signal in a different direction.
I actually have. I created back in a couple of years back. Created this series of episodes that I called "Make Wi-Fi Visible."
Oh, okay.
So maybe you can share that along with the episode where I created pictures of, those different behaviors, and I compared to lights, because light is also electromagnetic wave, so we can compare that to Wi-Fi, so we can better understand the behavior of the wave. So maybe you can share that as well.
Yeah, we'll add that to the show notes. The next one is scatter, which is just a reflection, but multiple reflections. So it's hitting a surface that scatters that signal into multiple different directions. And I think of this as like a disco ball. So if you shine a light at a disco ball, it's going to reflect that in many different directions. So you're standing in one place, you'll see light being hit all over the place off of that disco ball. In the real world, you're talking about things like a chain link fence. I've seen people put like a protection over APs, which happens to be metal, and so whenever the AP is transmitting, it's actually that signal is being scattered into different directions as it reflects off that mesh or that chain link.
Yeah, the comparison I was doing is if lights from the sun is going through a cloud, sometimes you can see different streams of lights.
Yeah.
It's kind of like the same idea.
Yeah, so that's scatter. And then you have diffraction, which I think happens a lot. And I've seen installations where this happens, where diffraction is, what's the best way to describe this?
It's a wave going around an object.
Yeah, there you go. So,
I guess, yeah.
And I don't know where I saw this, this analogy is where you have this river flowing. If you placed a large rock in that river, you'll see that the water is going to flow along the sides of the rock. But directly behind the rock, as the flow is moving, there's less current from the stream because of that, as the water is going around it. And it's very similar to in our Wi-Fi environments where if you place an AP, say, on the ceiling, but then very close to it is this pillar that's made out of concrete, that signal is going to bend around that concrete. But if there's somebody sitting on the other side of that concrete pillar, they're probably not going to get much signal unless it's being, say, reflected from a different angle. And
it's that's a really good example. I think about diffraction with pillars like this in building. Diffraction also works the other way around. If you have a closed opening, a small opening, the RF will go through this opening and will expand after the opening. See what I mean?
Yeah.
It's kind of like if you have light going through like a small opening. Let's say you have a door and you have a small opening because you need somewhere to put the key, like those old school type of doors. The light will still go through this hole, and the stream of light will expand as it goes inside the house.
Yeah, and there's like kitchen environments where if you've got Wi-Fi in a kitchen, and let's say they have this door that opens and closes because that's where they're serving food. I don't know if you guys can picture that, but Wi-Fi will go through that hole and spread out through that way because I've seen like in elementary schools where the kitchens have this metal door that goes down, right? It closes because they're not serving food anymore. But as it opens, then the kitchen will receive Wi-Fi signal from whatever's on the outside of that kitchen, and it goes through that door where they're serving food to the general, like the students. So like it depends on a lot of things. If you haven't walked the environment and you don't know that there's this metal door that opens and closes, and then whenever, let's say the door's closed and in the kitchen they're for some using an iPad, for example, to find out what food they're checking in to the kitchen, they might not be receiving that signal because the metal door's closed. And that's an example that of Wi-Fi not going through metal but reflecting. But when it's open, it's diffracting into that room.
So if you know about those RF behaviors, you analyze the space differently. Huh?
Yeah, exactly. And sometimes you won't need predictive software if you look at you understand the characteristics. You already have in your mind how that's going to propagate within the room.
Well, most predictive softwares only take attenuation into consideration.
Yeah, so
it would be too much math to do the rest, I think.
It is. And so if you're using things like Ekahau, you can measure different, or you can apply different materials that have different attenuation. So that's another behavior. There's attenuation is a loss of signal and decrease in amplitude. And attenuation could be going through a drywall, which could be 3 dB. So there's different examples of wall materials and their attenuation values. And this is something you have to measure in your environment, because a drywall could be very different in different buildings.
Yeah. Could be 2 dB, 3 dB, 4 dB, 5 dB. Yeah. Depending what you have inside the drywall, right?
You might not even know what's in the drywall. It could be drywall to you, but then if you cut out a hole, there could be brick inside.
Yeah, you're right. And sometimes you have multiple sheets of walls, dry walls, shear rocks.
Yeah.
And sometimes it's metal studs, sometimes it's wood studs, sometimes, I don't know.
And that's why we have to do wall attenuation measurements to understand what you would have to put into your predictive. If you're going to do a predictive design, how much of that signal are you going to lose between each wall? And so that's something that I like to do, is at least do some wall measurements where you don't have to do every single wall, but you might want to check out certain walls where you think might be different in say the first floor and second floor, or just in a different part of the building. So that's attenuation. And then we have multipath, which back in the day, let's say like 802.11a and B days, where multipath was very bad. But nowadays, since 802.11n, multipath can be used to a device's advantage when signal is actually being received from different paths. Multiple signals are taking different paths to get to the receiver. And there's components within the Wi-Fi chips to basically bring those signals together to try to determine what that signal actually is and demodulate it better.
Yeah, MIMO is taking advantage of multipath and those different, signals, out of phase signals, to pretty much send different type of information at the same time.
But then why would you consider multipath in your designs? And one of those reasons could be a warehouse, right? Francois, you do a lot of warehouse. Maybe those scanner guns don't support multipath very well because they're old devices.
Yeah, exactly. In a warehouse, depending on the typical warehouse with racks, you're going to have a lot of reflection. Mm-hmm. So if your device don't support multipath, you might have a lot of a signal that the device can actually not understand. So it will just it will just not reply, and then you're going to have a lot of retries, mm-hmm. and the overall RF environment will not look good.
Yeah.
So if you can find, scanners that supports it, that's the best. And you can take advantage of this reflection into your advantage.
Yep. And see how we tie different characteristics together. You have multipath, which is created either by reflection. It could be done by scattering. So that's pretty much the end of what we were discussing. But we talked about RF, wavelength, amplitude, the frequency, and the phase. And then also some of these behaviors that you'll see in an environment. That's reflection, absorption, refraction, scatter, diffraction, attenuation, and multipath. So it's kind of the entry-level method of learning RF and how you can apply that to your environment. I use this all the time whenever I'm walking a building or different structure or where Wi-Fi needs to be, and I'm looking at the different materials in the room and seeing how any of this would apply or affect the signal getting to the receiver.
Yeah, and we'll share a few pictures and diagrams so you can better visualize those behaviors as well.
Cool. Well, I want to thank you guys for listening to this episode. If there's anything you want to contribute to this conversation, head over to the show notes, cleartosend.net/130. If you have any questions or something that we didn't explain fully, we're more than happy to respond to you with images, because I think images will work very well in this type of discussion.
Thank you, Roel. And it's still raining here.
Still warm here. I'm going to go upstairs and turn on my AC. All right. Thanks, guys. We'll see you in the next episode.
See you, Roel. Thank you.